Hello everyone, this is the second part of electricity. Today we will discuss about electromagnetism. So let's get started. Firstly, whenever we want to discuss about magnetism, we have the magnetic substance. Magnetic substance is also referred to as ferrous materials, and these are the materials that are attracted to magnets and they can be magnetized. What do I mean by magnetized? Means that they will act as magnets. A bar magnet is an iron bar, but it has the ability to attract other objects that are made up of iron, steel, cobalt, and nickel. And you need to memorize those. So always remember that whenever you have a bar magnet, it will attract iron, steel, cobalt, and nickel. Moving on to magnetic poles. Magnetic poles are at the end of the bar magnet, and both have equal strength. One is the North Pole and the other one is the South Pole. This is an illustration of a normal bar magnet where it contains both of the poles, the North Pole and the South Pole. The compass needle is a small magnet. If a magnet is hanged freely, then its north will point to the north of the Earth and its south will point to the south of the Earth. So here's the compass, and as you can see in the compass, this is the magnet. So as you can see, if this compass is left freely or it's hanged freely, then therefore its north, because the magnet, we know that consists of north and south, so its north will point towards the north of the Earth and its south will point towards the south of the Earth. Always remember that like poles repel and unlike poles attract. So like poles, what I mean by like poles is north and north. They will experience a repulsion force. But unlike poles, like for example a North Pole and a South Pole, they will experience attraction force. And the force between magnetic poles, it decreases as their separation increases. Like for example, as I move the magnet, if I have here north and south, they're being attracted. If I move this magnet further away from the second magnet, my first magnet will experience less attraction to my second magnet, and vice versa. What's the reason is that as the distance or as the separation between those two magnets increases, the magnetic effect itself will decrease. Now let's move on to magnetization. We have different methods to magnetize things. Like for example, we can magnetize by induction, magnetization by stroking, and electric DC magnetization. So when we discuss about the magnetization by induction, is that when you bring any magnet closer to iron nails and paper clips, they will experience a force of attraction. If a strong magnet is used and soft iron rod is attracted to it, then the soft iron rod will acquire the magnetic property and therefore it can attract iron fillings strongly. What do I mean by this? Like for example, if you got a normal magnet, right? And this magnet is used to attract any soft iron rod, like for example this rod, or for example if you have the paper clips or anything, then what will happen to the soft iron rod or to the paper clips is that they will become magnetized. And as I've mentioned from before, they will act as if they're magnets. So therefore, they will also experience or they will also cause a force of attraction to other objects as well. And what I mean by other objects is that they need to be a ferrous material objects. Moving on to soft iron and steel. Soft iron, it's a soft magnetic material or a soft magnetic substance. It easily magnetizes and demagnetizes. But the steel, it's a hard magnetic substance. It's difficult to magnetize it and it's difficult to demagnetize it. A soft iron, very common example, is the electromagnets. As I've mentioned from before, this is used in making electromagnets. Electromagnets, for example, are used in the scrap yards. So whenever an electric current is flowing through the wires here in the electromagnet, it causes it to become magnetized and to create a magnetic field so that it's going to attract other magnetic substances. When we talk about a hard magnetic substance, it's therefore difficult to magnetize it and demagnetize it. It means that we can't control it, for example, by current, or we can't control it somehow. It will forever stay as a strong magnet. A very common example is the bar magnet. The bar magnet, once it's magnetized, it's difficult to demagnetize it back. and therefore it can hold its magnetic property for a longer time compared to the electromagnets. Moving on to magnetization by stroking is that when the steel bar is stroked by a magnet, using the same pole in the same direction, and therefore the pole produced at the first end is similar to the stroking pole. Like for example, if you got this magnet and you're stroking the steel bar, you're stroking the magnet against the steel bar using the north pole, then therefore this end that will be created here is going to be north pole, and the other end here is going to be the south pole. And vice versa. For example, if I flipped this magnet and I used the south pole instead to stroke the steel bar, therefore the pole that will be created here is going to be south, and the other pole here is going to be north. Moving on to electric DC magnetization is that when a connecting wire to a DC battery, the wire will become magnetized and it's going to create magnetic field lines, and therefore this will attract magnetic materials. And as I've mentioned from before, magnetic materials are like iron, cobalt, nickel, and steel. Here we call this as an electromagnet. Yes, we did mention this from before here in this part. So the polarity of a magnet is given by the right hand grip rule. What do I mean by the polarity of the magnet? Like for example, is that once you curl your fingers around the coil or around the wire, therefore the outstretched thumb is going to show you the polarity. Like for example here, the thumb will always point towards the north pole. In this case, here is going to be north, and here is going to be south. Now always remember that the strength of the electromagnet is increased by larger value of current and when you increase the number of turnings of the solenoid. So make sure to memorize these. Moving on to magnetic field experiments, we're going to discuss about the magnetic field itself. It's a space created around the magnet that causes the magnetic effect. Magnetic field lines always, they move from north pole to south pole. Talking about the magnetic field experiments, the first one you should take into consideration is the iron fillings method. Is that when you get a bar magnet and then you put a sheet of paper on top of the bar magnet. Sprinkle iron fillings evenly on the top of the paper and then tap the paper gently, and the fillings, they should form patterns of lines. These lines, they represent the magnetic field lines. This experiment, it does not show you the direction of the magnetic field, but it only shows you the shape of the magnetic field. If you realize that here in this part, it's a bit denser compared to this part. What's the reason is that because this part, the iron fillings here are closer to the poles. Usually the magnetic effect, the magnetic field effect or the magnetic force is greatest near the poles. But as we move further away from the poles, here we're going to experience lower magnetic force compared to here. Moving on to the compass experiment is that when you place a bar magnet on top of a paper, so already we have here the paper ready, and then I got the bar magnet and placed it on top. Then after that, you're going to place the compass next to the north pole. Okay, here next to the north pole. Mark a dot where the compass points. So here, this is the first dot. Put the compass next to the marked dot and then repeat several times until you reach the other pole. Connect the dots to form magnetic field lines, and then after that you're going to repeat it for the other lines as well. When we discuss about the magnetic field direction, it's the direction of the force on the north pole of the magnet placed at this point. Here we have different magnetic field shapes. This is the magnetic field of a bar magnet. As you can see that the magnetic field always moves from north to south, There's going to be outwards and inwards. Magnetic field between unlike poles, we're going to experience a force of attraction. And then the magnetic field between like poles, so we experience repulsion. Here south, and here we have north and north. Properties of magnetic field lines. Always remember that the lines, they go from the north pole to the south pole, and always remember that whenever you're drawing the magnetic field lines, make sure that the lines, they will never cross. When the lines are closer together, this will indicate that we have a strong magnetic field. So in this case, as you can see, we have here a very strong magnetic field. Why? Because the magnetic field lines are a bit closer, or they're very close together compared to here. Then, when the lines are far apart from each other, this will indicate that we have a weak magnetic field. Magnetic force is strong near the poles, as I've mentioned from before. So near the poles, always we're going to have a very strong magnetic field compared to here and here. Now moving on to uniform magnetic fields. Uniform magnetic field means that the magnetic field lines, they are parallel and they are equally spaced. Okay. Going on to the relay it's used to control large current in a large circuit from a small current in another circuit. The first circuit, it would have a solenoid so that when a small current passes in the first circuit in the solenoid, it will become magnetized. And therefore, this will attract the iron armature in the second circuit, and it causes the circuit to close and larger current to flow in the second circuit. As you can see, we need to have a coil or a solenoid. So, when the current is on, it causes this coil to become magnetized and to become an electromagnet, which will attract the iron armature in the second circuit, and therefore this will cause larger current to flow in the next circuit and causing the components in the second circuit to switch on. DC motor. So, let's get started firstly with a wire. Any wire that has an electric current, it will have a magnetic field. So any wire into which current flows, it will create a magnetic field around it. If the current direction changes, then also the field direction will also change. To identify the change, we will use the right-hand grip rule. The direction of the thumb, upwards or downwards, is going to indicate the magnetic field direction by the remaining fingers, clockwise or anti-clockwise. Like for example, in this case, since the current is moving upwards, then therefore the thumb will also move upwards. And therefore, the magnetic field direction is going to be this way, which means it's going to be anti-clockwise. So here, if the current moves downwards, then the thumb will point downwards, and the magnetic field lines are going to move clockwise. Moving on to the solenoid. The solenoid also produces a magnetic field which is similar to the bar magnet. We're going to use the right-hand grip rule, where the solenoid is gripped in the current direction, and then the thumb will point towards the North Pole. Magnetic field lines are stronger and closer inside the solenoid compared to the outside. How to vary the magnetic field strength. Always remember that the magnetic field strength is going to decrease as the distance increases. And the field lines, they will spread out as the distance increases. Increase the current, it strengthens the magnetic field, and the field lines, they will become closer together. When you reverse the current direction, it only reverses the direction of the magnetic field. But the strength is going to remain the same. You need to keep that in mind, that only when reversing the current direction, it reverses the direction of the magnetic field, but the strength will be the same. Components of a DC electric motor. So this is the DC electric motor. When we discuss about the components, it just has a rectangular coil, as you can see, which is fixed up on an axle that can rotate. Then we have a magnet which provides the magnetic field. We have here, this is the magnet, and this is the one that provides the magnetic field. We have the split ring commutator, which reverses the current every half cycle so that to ensure we have a complete rotation of the coil. And we have the brushes. These are the carbon blocks which are pressed against the commutator to supply current continuously. How does the DC motor operates? So when we have direct current that flows through the coil, this will cause magnetic field. So as we have a current that flows through this rectangular coil, it causes the rectangular coil to have its own magnetic field. And this magnetic field of the coil will interact with the magnetic field of the magnet. Therefore, this will cause a force. This force will create a turning effect which causes the coil to rotate. The split ring commutator, it reverses the direction of the current every half cycle, making sure that the coil continuously rotates in the same direction. We use Fleming's left-hand rule in case of a DC motor. So here, the thumb represents the motion or the force, and we have the index finger. It indicates the magnetic field, and the middle finger, it indicates the direction of the current. Moving on to the AC generator, the components of the AC generator is the rectangular coil, which is positioned between the poles of the magnet. And this is something in similarity with the DC motor. Then we have the slip rings. Instead of the split rings which are used in the DC motor, in the AC generator we use slip rings, which are connected to the ends of the coil and they rotate with the coil. Then we have the carbon brushes. They have the same function, which are pressed against the slip rings, and then they're used to conduct the current. How does the AC generator operates? Now here we do not use a DC current. Instead here we use an AC current, which means an alternating current. So the EMF, it varies as the coil moves. In the vertical position, there is no EMF as the coil cuts the least number of magnetic field lines. When we have the vertical position, it won't cut. It moves in parallel with the magnetic field lines, and therefore it cuts the least number of magnetic field lines. But in the horizontal position, it's going to cut the magnetic field lines perpendicularly, and this will cause a maximum EMF. The direction of the EMF, it reverses as the coil continues to rotate, which produces an alternating current in the circuit. The frequency of the AC is determined by the rotation speed of the coil. The faster the coil rotation, the higher the frequency. In this case, for an AC generator, we use Fleming's right-hand rule instead of Fleming's left-hand rule. Moving on to transformers. A transformer consists of primary and secondary coil on a soft iron core. So here we have a soft iron core, and here we have a primary coil and a secondary coil. When an AC current is supplied to the primary coil, this will cause an alternating magnetic field in the primary coil. This alternating magnetic field is going to be carried by the soft iron core from the primary coil to the secondary coil. And therefore, the secondary coil is going to cut the changing magnetic field in the soft iron core, which induces an EMF in the secondary coil. So the AC current, it will be transmitted from the primary coil to the secondary coil. Here are some transformer equations that you need to know. The alternating voltage supplied to the primary, it will induce an alternating voltage in the secondary. And this is the relationship is given by Vp over Vs equals to Mp over Ns, which means that the voltage in the primary divided by the voltage in the secondary equals to the number of turns in the primary coil divided by the number of turns in the secondary coil. Also, the Pn equals to Pout, which means that the power into the coil equals to the power out of the secondary coil, which means we know that P equals to Vi, so Vin into In equals to Vout into Iout. Types of transformer, we have two types of a transformer. We have a step-up transformer and a step-down transformer. Whenever we want to discuss about the step-up transformer and step-down transformer, we will identify them according to the secondary coil, the number of turns in the secondary coil. The more number of turns in the secondary coil and fewer turns in the primary coil, therefore this causes the voltage to increase, which means that this is a step-up transformer. But the step-down transformer, we're going to have less turns in the secondary coil and more turns in the primary coil, so therefore the voltage decreases. So in order to solve the power loss, instead of changing the wires of the pylons all around the city, which might be very expensive, instead we thought about decreasing the current. Because as we decrease the current, the voltage increases. So decreasing the current of transmitting electricity is the most reasonable solution in order to decrease the problem of power loss, which we mean as heat loss. So when the current decreases, the voltage increases, and vice versa. If the current increases, the voltage decreases. Moving on to Lenz Law, that any moving magnet is considered a changing magnetic field. If you move this bar magnet near a solenoid, therefore this bar magnet to the solenoid, it acts as a changing magnetic field. So when any coil is exposed to a changing magnetic field, this will induce a current in the coil. The current induced, it will oppose the changing magnetic field that caused it. This is Lenz Law. So any current induced in the coil or in the solenoid, it will try to oppose the changing magnetic field that caused it from the very first place. For example, if the magnet is moving towards the coil with a north pole, what does it do? It induces a current in the coil, but this current, it will flow in a direction that will create a north pole in order to repel the magnet and to oppose its motion towards the coil. So as if the coil says to the magnet that if you want to enter, I won't let you. And if you want to leave, I won't let you. So instead, if the bar magnet is trying to enter the coil, it will try to repel it. And if it wants to leave the coil, it will attract it. Moving on to how the loudspeaker functions. The loudspeaker, it converts the electrical signals into sound waves. Varying the current passes through a coil placed in a magnetic field, and this magnetic field, it will interact, causing the coil to vibrate. Therefore, the vibrations, they create sound waves in the surrounding air. So for example, if we have a varying current, which means an alternating current, passes through the coil here, this causes the coil to have its own magnetic field. The magnetic field of the coil will interact with the magnetic field of the bar magnet, and therefore this will cause a force. This force is represented in the form of vibrations, which create sound waves in the surrounding air. So whenever we have two magnetic fields interacting together, they will always cause a force. Thank you guys for watching, and I will be attaching the link for these notes in the description, so make sure to check it out. Thank you so much and wishing you all the best.